Here we're going to review how to solve conservation of energy problems. We're going to use the following procedure. First, we're going to draw a schematic representation of the system that we're using. Then we're going to identify the different states the system is in and the types of energy involved. And we're going to put that all and show how they're all distributed in each of the states by making a table. And then we're going to use the fact that the total amount of energy stays the same. We're going to do this by considering the following example. We're going to have a block sitting on the top of a ramp. It'll start at rest, and there'll be a spring at the bottom of the ramp. And we're going to basically find what is the maximum speed that the block attains as it slides down the ramp, and what is the maximum compression of the spring. For our purposes, the ramp will be frictionless, and this is a little bit of an involved problem because we're going to have lots of different types of energy that are involved. So this is a fairly complicated conservation of energy problem to show how the procedure can be used to solve even a more involved problem. So first thing we're going to do is take this system and draw a schematic diagram of it. The system consists of three basic pieces. We have the ramp, and the ramp has a spring on it. We have the block that will be moving, and then we also have the earth, which will be providing a gravitational force and also will be our frame of reference. So we have the block that is interacting with the ramp via a spring, and also there's a normal force between the block and the ramp. And finally, there's the gravitational force between the block and the earth. Once we've drawn this diagram, what we can now do is look at each of the interactions and ask what types of energy, if any, are involved. So one interaction is the spring, and of course that has elastic potential energy. The normal force will not do any work because it'll be applied perpendicular to the motion, so it will not convert one type of energy into another type, nor will it store any energy. So the normal force does not involve any types of energy. We have gravity, and of course gravity has gravitational potential energy. The things that might have kinetic energy are only the block, that's the one mass that will be moving, the ramp is stationary, and the earth provides our frame of reference. While the spring will be moving, we will take the spring to be massless, and therefore it will have no kinetic energy. Now that we have our types of energy, now we can look at the different states that this system will be in and make a table to organize our work. We will have three different states. Our initial state, where the block will start at the top of the ramp at rest. Our final state is when the block is again at rest and the spring is compressed. Then we also have a middle state where we're looking for the maximum speed, which will be when the kinetic energy is at its maximum. It also will be when the net force equals zero. And sometimes we do have to be careful to make sure we understand what the conditions are for each of the states. This is when the block starts at rest, this is when the block ends at rest, and this is when the net force goes to zero. The rows that we've put in are each of the different types of energy: the kinetic of the block, the gravitational potential energy, the elastic potential energy. The bottom here is the total amount of energy. Now, the kinetic energy will be zero when the block is at rest with respect to the earth, because the earth is our frame of reference. We will define the spring to have no energy when it is neither compressed nor stretched. However, the gravitational potential energy we need to be careful with because we can put our origin wherever we want. But once we place it someplace, we need to be consistent. For this problem, I'm going to put the origin at the top of the uncompressed spring. Any place above here, the gravitational potential energy will be positive. Any place below there, namely when the spring is compressed, the gravitational potential energy will be negative. So we need to remember, any place down here, we have negative gravitational potential energy. Any place up here, it's positive. Now what we can do is take and fill in all of these boxes in our table. And that's what I've done here. So at the initial state, that's fairly straightforward. The kinetic energy is zero. The spring has not been touched yet, so that's still no potential energy. We start with gravitational, and that's the mass times g. L sine theta is how high up it starts. And all of those numbers we know, we plug them in, we can calculate the total amount of energy. And that stays the same all across. So once we've calculated in the initial state, we know how much we must have in the middle state and at the final state. Now let's consider the middle state. This is where we have our maximum speed. So the block is moving. It has kinetic energy of 1/2 mv squared. But we also need to have the net force to be zero. So let's consider the forces acting on the block. As it slides down the ramp, It has gravity pulling it down, and it has two components, one parallel to the ramp and one perpendicular to the ramp. The normal force will cancel out the component perpendicular to the surface, but that leaves the component parallel to the surface untouched. So the spring has to be compressed in order to counterbalance this component of gravity. So we do need to have the spring being compressed in order to have the net force go to zero. And how much does it have to be compressed? Well, so that mg sine theta must equal k times d, the amount the spring is compressed. This will tell us how much the spring needs to be compressed for the net force to be zero. So that means we must have some elastic potential energy at this point. So that's 1/2 kd squared. And we have some gravitational potential energy. It is negative because we are now below the origin by a distance d along the ramp. So the height is d sine theta. So we can take and add all these up, set them equal to the total amount of energy, and solve for the velocity. And that will be the maximum velocity. Now, the final state, we have no kinetic energy. That is zero. We do have the spring being compressed by some distance d, 1/2 kd squared. We also have some potential energy, and it's negative because we're below the origin, so that'll be mg capital D sine theta. We now again have an equation we can solve for the amount of compression at the end state, which is capital D.